Imagine standing beneath a quiet night sky. There is no movement, no sound, just silence, and light that has travelled for millions of years to reach your eyes. The stars look still, predictable, peaceful, but that feeling is an illusion. Because somewhere in that darkness, hidden among ordinary-looking stars, there exists an object so extreme that it does not just challenge physics. It actively breaks the rules we thought were unbreakable. A dead star, barely 20 kilometers across, yet powerful enough to distort space, tear apart atoms, and unleash more energy in a fraction of a second than our sun will produce in 100,000 years. And when it erupts, it does not do so quietly. In a fraction of a second, it can release more energy than our sun will produce in 100,000 years. This is not a black hole. This is something else. Something stranger. Something more violent in ways that are harder to imagine. This is Magnetar. And what you're about to explore is not just a story about space. It is a story about the limits of reality itself. There is a very specific kind of silence that fills a control room when something impossible appears on the screens. It is not confusion. It is not panic. It is quiet that comes when the data is too precise to ignore. Numbers begin to rise, instruments begin to spike, and yet everything is functioning perfectly. That is what makes it unsettling. Because when machines agree with each other this clearly, it usually means one thing. Something real has just happened. That moment arrived on December 27, 2004. Without warning, space-based observatories began detecting an intense burst of gamma radiation. Satellites from different missions positioned all around Earth recorded the same signal almost simultaneously. These included instruments designed to monitor high-energy cosmic events, missions built specifically to catch the most violent explosions in the universe. At first glance, scientists assumed it was a gamma ray burst, one of the powerful flashes typically caused by collapsing massive stars or merging neutron stars in distant galaxies. But within minutes, something did not add up. The signal was too strong, too close, and most importantly, its origin was not billions of light years away, but from within our own galaxy, the Milky Way. The source was quickly identified. A known object already catalogued and studied, a magnetar called SGR 1806-20, located roughly 50,000 light-years from Earth in the direction of the constellation Sagittarius. This was not an unknown explosion. It was something far more unsettling. It was a familiar object behaving in an unfamiliar way. When scientists began analysing the energy released during that brief moment, the results were almost difficult to accept. In just 0.1 to 0.2 seconds, this magnetar emitted as much energy as the Sun produces over approximately 100,000 years. To understand that scale, consider this. The Sun releases energy continuously, every second, through nuclear fusion. It powers the entire solar system, drives Earth's climate, and sustains life. And yet, this dead star, no larger than a city, released an equivalent amount of energy in a fraction of a second. The event is now known as a giant flare, one of the most powerful types of eruptions a magnetar can produce. It began with an intense spike of gamma rays, followed by a tail of radiation that pulsed for several minutes, matching the magnetar's rotation. What made this event extraordinary was not just its energy, but its effect on Earth, despite the immense distance. Even from tens of thousands of light years away, the burst was strong enough to interact with our planet's atmosphere. It ionized the upper layers of the ionosphere, temporarily altering its structure. This layer is critical for radio communication, as it reflects and modifies radio waves used for long-distance transmission. As a result, scientists observed measurable disturbances in radio signals across the planet. Some satellites were briefly overwhelmed by the intensity of the radiation, forcing instruments to shut down or saturate due to the sheer energy input. For a brief moment, less than a second, Earth was directly affected by an event that occurred halfway across the galaxy. Not by debris, not by shock waves, but by pure energy. What makes this even more remarkable is how narrowly Earth avoided something far more serious. If a magnetar like SGR 1806-20 was significantly closer within a few thousand light years, the effects could be far more severe. A flare of this magnitude could damage satellites, disrupt global communications, and potentially affect atmospheric chemistry in ways that could impact life on Earth. But in this case, distance protected us. Still, the realization remained. A dead star only about 20 kilometers wide had released a burst so powerful that it could be detected across the galaxy and still influence our planet. It did not explode like a supernova. It did not collapse like a black hole. It simply cracked, its magnetic field shifting, its crust fracturing, and in doing so it released a fraction of its stored energy. That is what made scientists pause. Because if this was only a fraction, what would the full power of such an object look like? In that brief moment in 2004, the universe revealed something important. Not loudly, not dramatically, but clearly. That even the smallest objects under the right conditions can become the most powerful forces in existence. And for a fraction of a second, we felt it. To truly grasp the nature of a magnetar, we must journey to the final moments of a massive star's life. Not millions of years ago, but the brief, violent seconds when stellar equilibrium collapses under the weight of gravity. Stars, for the majority of their lives, exist in delicate balance. Gravity constantly pulls matter inward, trying to crush the star into oblivion, while nuclear fusion pushes outward, converting lighter elements like hydrogen and helium into heavier ones, and generating the pressure needed to hold the star's mass aloft. This tug of war can last for millions to billions of years, but eventually the star's fuel runs out as the hydrogen, helium, and later heavier elements are fused into iron. Fusion slows, unable to counteract the inward pull of gravity. When the balance fails, the core collapses catastrophically. In less than a second, matter is compressed to extreme densities. Electrons are forced into protons, forming neutrons in a process called electron capture, leaving behind a dense, compact neutron core. This is the birth of a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Its gravity is immense, compressing atoms into nearly incomprehensible states of matter, creating one of the universe's most exotic objects. But the story does not end there. As the core collapses, the outer layers of the star rebound violently, exploding outward in a brilliant supernova that can outshine entire galaxies for weeks. This explosion disperses elements forged into the star's heart, oxygen, carbon, iron, into the surrounding space, seeding the galaxy for future generations of stars and planets. What remains at the centre is small, dense, and dead, but it is far from quiet. Most neutron stars are already extreme. They spin rapidly, sometimes hundreds of times per second, and emit beams of radiation detectable as pulsars. They have magnetic fields billions of times stronger than Earth's, twisting the space around them. But some of these neutron stars take the extremity even further. A select few develop magnetic fields so powerful they break the laws of physics as we normally understand them. A magnetar is, in essence, a neutron star on steroids. While a typical neutron star already exerts phenomenal forces, a magnetar amplifies its magnetic field to unprecedented levels, reaching as high as 10 to the 15th power Gauss, a quadrillion times stronger than Earth's magnetic field and 1,000 times stronger than ordinary neutron stars. At these magnitudes, magnetic forces dominate over gravity, radiation pressure, and even the chemistry of atoms. Electron clouds stretch into elongated needles. Chemical bonds are torn apart and matter itself begins to behave in ways that defy conventional understanding. Creation of such a magnetic leviathan is no accident. During the collapse of the progenitor star, rapid rotation and convection in the proto-neutron star act like a dynamo, winding up the magnetic field lines into a twisted, hyper-intense network. Energy is trapped in these fields equivalent to a planet's entire mass, converted into pure energy, waiting to be released in bursts that can be detected across galaxies. In short, a magnetar is not just a dead star, it is a city-sized furnace of gravity, magnetism, and quantum extremes, a living laboratory of physics pushed to its limits, where a neutron star bends the rules of matter, a magnetar shatters them, giving astronomers a rare window into phenomena that cannot be recreated in any terrestrial laboratory. In the universe's catalogue of extremes, magnetars stand apart, not for their size, but for their sheer power, their ability to manipulate space, matter and energy in ways that seem almost magical, yet are entirely real. They are the ultimate cosmic monsters, small, dense, dead, and yet unimaginably alive in their influence on the cosmos. Neutron stars are already among the most extreme objects in the universe. Born from the collapse of massive stars, they spin at incredible speeds, emitting beams of radiation that sweep across space like cosmic lighthouses. Their magnetic fields are immense, billions of times stronger than Earth's, powerful enough to bend charged particles and influence surrounding matter. Yet, in a rare few, nature takes this extremity even further. These rare stars become magnetars, objects so powerful that they defy the very laws of physics as we understand them. The difference between a typical neutron star and a magnetar is not just one of strength, it is scale. While an ordinary neutron star's magnetic field may reach billions of Gauss, a magnetar's field can soar to 10 to the 15th power Gauss, a quadrillion times stronger than Earth's magnetic field. To put that in perspective, Earth's magnetic field, which shields us from solar and cosmic radiation, is only about 0.5 Gauss. A common refrigerator magnet is roughly 100 Gauss. Even the strongest MRI machines humans can build reach only a few tens of thousands of Gauss. The magnetar, by comparison, is trillions of times more powerful than any magnetic field we can generate on Earth. And at these magnitudes, magnetism stops acting like a simple, familiar force. At this level, the magnetic field becomes the dominant influence in the star's vicinity, bending and warping reality itself. Atoms cannot retain their usual shape. Their electron clouds are stretched into elongated needles. Chemical bonds break spontaneously, and matter behaves in ways utterly alien to our experience. Even in the empty space, the vacuum that seems featureless and inert is not untouched. Quantum physics tells us that the vacuum is never truly empty. It is a raging froth of virtual particles, continuously appearing and crushing each other in the blink of an eye. Under normal conditions, this quantum foam is imperceptible. But near a magnetar, the magnetic field is so extreme that it directly affects these quantum processes. One of the most astonishing phenomena that arises in the presence of a magnetar is vacuum birefringence. In essence, space itself acts like crystal. Light passing through the magnetar's magnetic field splits into different polarization states, each travelling at slightly different speeds. This effect, long predicted by quantum electrodynamics, QED, had never been observed directly until astronomers measured the light from magnetars in X-ray wavelengths. For a brief instant, photons do not travel along straight lines as they would in ordinary space. They bend, split, and are polarized, creating one of the rarest and most extreme examples of physics in action anywhere in the universe. This is not science fiction. It is real, observable, and measurable. Magnetars are unique laboratories of nature, pushing the boundaries of what physics can explain. They show us that magnetism can rival gravity in shaping the universe, that space itself is pliable under extreme conditions, and that the cosmos still holds phenomena that challenge even our most confident theories. A magnetar does not just exist in space, it reshapes it, bending light, twisting atomic structure, and revealing the limits of reality as we know it. In short, a magnetar is not simply a powerful star. It is a cosmic force of nature, where magnetism dominates, matter behaves unnaturally, and quantum physics becomes visibly, tangibly real. To stand near one, even in imagination, is to confront a power that breaks the rules of physics itself, a living reminder that the universe is far stranger and far more extreme than our everyday experiences could ever suggest. To truly grasp the magnitude of a magnetar's power, we need to start with something familiar: Earth's own magnetic field. This invisible shield protects life from harmful solar winds and cosmic radiation. Without it, our atmosphere would be constantly bombarded by energetic particles, and life as we know it would struggle to survive. Now imagine taking that protective field, not increasing it tenfold, not 1,000,000 times, but trillions of times stronger. That is the scale we are talking about at the surface of a magnetar. At this level of magnetism, matter itself begins to behave in ways completely alien to our understanding. Atoms, normally spherical and stable, are stretched into elongated shapes. Their electron clouds forming needle-like structures. Chemical bonds, the glue that holds molecules together, break almost instantly. Proteins unravel. DNA strands tear apart, and even the fundamental chemistry that makes life possible ceases to function. This is not heat, it is not pressure. It is a force so dominant that it can reshape matter at a molecular level without physical contact. Yet, the true strangeness goes even deeper. The vacuum of space, the empty void between stars, is not empty at all. According to quantum electrodynamics, QED, it is filled with virtual particles constantly flickering in and out of existence. Normally, this quantum foam is imperceptible, with a hidden background to the cosmos. But near a magnetar, the magnetic field is so extreme that it interacts with these virtual particles directly. Space itself begins to act as a physical medium, not a void. The most remarkable consequence of this interaction is a phenomenon known as vacuum birefringence. Light passing through the magnetar's magnetic field splits into different polarization states, travelling at slightly different speeds. It bends, refracts, and behaves as though it were moving through a crystal rather than through empty space. This is one of the rare instances where a fundamental prediction of quantum physics can be observed on a cosmic scale, turning the Magnetar into a natural laboratory for the most extreme physical conditions in the universe. In other words, a magnetar does not simply exert influence on nearby matter, it alters reality itself. The vacuum becomes tangible, light bends, atoms stretch, chemistry fails. Physics, as we experience it on Earth, is no longer the rule. It is the exception. Standing or imagining standing near one is to witness the universe's raw, unrestrained power, a force that is beyond anything humans can create or survive. A magnetar teaches us that the cosmos is not just vast and distant, but radically different, where the ordinary laws of matter, energy, and space break down. It is a reminder that the universe is not only stranger than we imagine, but it is stranger than we can imagine. At first glance, a magnetar seems almost unremarkable. Compared to the giants of the cosmos, stars are hundreds of times larger than the Sun. They are tiny. Most magnetars measure only about 20 kilometers across, roughly the size of a large metropolitan city. If you tried to place one over a city like New York or Tokyo, it would barely cover the urban sprawl. Yet within this seemingly minuscule volume lies more mass than our Sun. Matter is compressed to densities so extreme that a single teaspoon of magnetar material would weigh billions of tons. The gravity on its surface is incomprehensible. For comparison, Earth's gravity is 9.8 meters per second squared. On a magnetar, the surface gravity reaches roughly 200 billion times that of Earth. Any object or human would be flattened instantly, crushed as though it were paper beneath an unstoppable cosmic press. But here lies the shocking truth. Gravity, for all its enormity, is not the greatest danger posed by a magnetar. The true danger comes from its magnetic field. A magnetar's magnetic field is staggering, measuring up to 10 to the 15th power Gauss, a quadrillion times stronger than Earth's. To put that in perspective, a refrigerator magnet is about 100 Gauss, and the strongest MRI machines reach tens of thousands of Gauss. The magnetar outclasses them all. This magnetic dominance extends far beyond its surface. Even at a distance of 1,000 kilometers, an invisible force of destruction radiates outward. Electronic devices would be instantly fried, compasses would spin wildly, losing all orientation, and atomic structures would begin to unravel. This is not theoretical. At this proximity, the Magnetar's field is strong enough to literally tear molecular bonds apart, stretching electrons and nuclei in ways that defy chemistry. Proteins would denature, DNA would break and matter itself would lose coherence. Heat or physical impact is not required. Simply being near the magnetar well outside its surface would be sufficient to annihilate life and disrupt matter on a molecular level. In essence, a magnetar transforms a city-sized sphere into a cosmic weapon of unimaginable power, where mass, gravity and magnetism converge to warp reality. It challenges our perception of size versus influence. Tiny in scale, yet enormous in effect. The Magnetar demonstrates that the universe's deadliest forces do not always come from giants like stars or black holes. Sometimes, the most extreme objects are small, dense and invisible, until they scream across the cosmos. Magnetars are among the most extreme objects in the universe, but they are far from stable. Their magnetic fields are so immense that they don't just influence the space around them, they exert colossal forces on the star itself. Inside a magnetar, the magnetic pressure twists and contorts the dense matter, placing incredible stress on its outer shell, the crust. Unlike Earth, where the crust is composed of rock and floats atop a molten mantle, a magnetar's crust is made of diamond-hard iron over a superfluid neutron interior. It is rigid, but the magnetic field stretches it in ways that no material on Earth could ever endure. Over time, the stress accumulates. Twisted magnetic lines pull at the crust like invisible cables being stretched to their breaking point, and then, inevitably, something has to be given. The crust fractures. The result is a starquake, a cosmic-scale rupture far more violent than anything experienced on Earth. Unlike earthquakes, which release energy gradually through seismic waves and aftershocks, a magnetar's starquake can unleash trillions of times more energy in an instant, concentrated in gamma rays and X-rays. When the crust shifts, the magnetic field snaps into a new configuration in a process called magnetic reconnection. This event accelerates charged particles to near-light speed along the field lines, generating a cascade of high-energy radiation. These bursts are known as soft gamma repeaters, SGRs, because they repeat over time, producing flashes detectable across the galaxy. Most SGR bursts are relatively small, lasting only fractions of a second, but even these minor outbursts carry enough energy to briefly rival the total output of the Sun. Occasionally, however, the starquake reaches a critical threshold, and the result is a giant flare. These rare, cataclysmic events are so powerful that they can be observed from tens of thousands of light-years away. One of the most famous examples occurred on December 27, 2004, when SGR 1806-20 released a burst of energy so intensely it temporarily ionized Earth's upper atmosphere, disrupted radio communications, and overwhelmed gamma-ray detectors across the planet. The star itself didn't explode, it simply cracked. Yet in that instant, the stored energy of decades, perhaps centuries of magnetic stress was released in a cosmic heartbeat. Starquakes illustrate a chilling truth. Magnetars are living laboratories of extreme physics, where gravity, nuclear density and magnetic fields collide. Each flare, each quake, teaches scientists about the behaviour of matter under conditions impossible to replicate on Earth. And for those observing from afar, these starquakes serve as a reminder that even a dead star can erupt with force, capable of reshaping the very space around it. Perhaps the most unsettling feature of a magnetar is not what it does to matter, but what it does to light itself. In ordinary space, light travels in straight lines, bending only under the influence of gravity. Photons, massless carriers of energy, obey the rules of classical physics and quantum mechanics alike. But near a magnetar, these rules start to bend, literally. The magnetic field of a magnetar is so powerful, up to 10 to the 15th power Gauss, a quadrillion times stronger than Earth's, that it can influence the vacuum of space. According to quantum electrodynamics, QED, empty space is never truly empty. Instead, it teems with virtual particles, constantly appearing and disappearing in what scientists call quantum foam. Normally, this quantum activity has no observable effect. But under the immense magnetic forces of a magnetar, the vacuum becomes a physical medium. It can split light, bend it, and slow it in specific ways, a phenomenon known as vacuum birefringence. What does this look like? Imagine a single beam of light entering the magnetar's magnetic field. Instead of travelling straight, it separates into two polarized components, each moving at slightly different speeds. Photons, the very quanta of light, behave as if travelling through a crystal, not empty space. This is more than theory. Astronomers using instruments such as the Very Large Telescope, VLT, have detected polarization in X-rays consistent with predictions, providing direct evidence that magnetars bend reality in ways that cannot be replicated on Earth. This is not just a quirk of nature, it is a rare opportunity to witness quantum physics on a cosmic scale. The universe, through Magnetars, offers a laboratory where the predictions of extreme QED can be observed directly, validating theories about light, magnetism, and the very structure of space itself. In essence, a magnetar doesn't just break the rules, it rewrites the way the universe behaves at the most fundamental level. To understand the terrifying might of a magnetar, we must return to the moment of its birth. Not every neutron star becomes a magnetar. In fact, the conditions required are so precise that only a tiny fraction, perhaps 1 in 10,000, achieve this level of cosmic ferocity. It begins with the death of a massive star, often 15 to 25 times the mass of our Sun, collapsing under its own gravity. In those final seconds, the star's core compresses to nuclear densities, forming a neutron star. But if this core is spinning exceptionally fast, a remarkable process takes hold. Conservation of angular momentum, like a figure skater pulling in her arms, causes the newborn neutron star to rotate hundreds of times per second. This rapid spin fuels an internal convective dynamo, twisting and amplifying the star's magnetic field to mind-bending intensities, reaching 10 to the 15th power Gauss. The energy stored in this magnetic field is staggering. To put it into perspective, the total magnetic energy of a magnetar is roughly equivalent to the mass energy of a small planet. It's not just strong, it is unstable. This immense field is constantly twisting, writhing, and stressing the star itself, storing a buildup of energy that can only be released in violent bursts. Over time, the magnetic field slowly decays, but while it is active, it dominates everything in the star's vicinity. This is a force that governs the star, shapes its behaviour, and occasionally unleashes catastrophic gamma-ray flares across the galaxy. Magnetars are, in essence, cosmic pressure cookers, born in a perfect storm of mass, spin, and magnetic chaos, existing as one of the universe's most extreme laboratories. Magnetars are not eternal. Their extraordinary power, while awe-inspiring, is temporary. Over time, the immense magnetic fields that define them begin to decay. This decay is gradual, taking thousands to tens of thousands of years, but it changes everything about the star's behaviour. As the magnetic field weakens, the violent X-ray and gamma-ray burst that once erupted unpredictably become less frequent, less energetic, and eventually fades into quiet. The star itself does not vanish, it simply transforms. What was once a hyperactive, universe-defying powerhouse, becoming an ordinary neutron star, still dense and extreme, but far less dangerous. During their active lives, magnetars are among the most volatile objects in the cosmos. A single magnetar has the potential to unleash energy bursts capable of affecting nearby star systems, even in extreme cases, ionizing atmospheres and disrupting electronics across light years of space. The energy released in a single giant flare, like that of SGR 1806-20 in 2004, outshone all the stars in the Milky Way for a fraction of a second, a reminder of the catastrophic potential these objects harbour. Currently, astronomers have identified roughly 30 active magnetars in our galaxy, scattered across the Milky Way's spiral arms, but that is likely only the tip of the iceberg. Many more remain dormant, hidden among billions of ordinary stars, quietly waiting for the right conditions to awaken their magnetic fury. Each known magnetar is a living testament to the violent death of massive stars, a cosmic scar left behind when fusion can no longer oppose gravity. Their existence shows that stellar death is not always silent. Sometimes, it leaves behind objects so extreme that the universe itself seems to bend in response. In essence, magnetars are not just remnants of dead stars, they are time-limited laboratories of extreme physics, where the laws of matter, magnetism, and quantum mechanics collide. Their fleeting lifetimes are measured not in the calm centuries of ordinary stars, but in the tense, violent millennia of magnetic chaos, reminding us that the universe is capable of creating forces far beyond human comprehension. The question of whether a magnetar could impact Earth is not just a thought experiment, it is a very real scientific consideration. While the universe feels vast and our planet relatively isolated, the sheer energy output of a magnetar is so extreme that distance is often the only thing standing between us and catastrophic effects. If a magnetar were located within approximately 10,000 light-years, and its violent flare happened to be pointed directly at Earth, the consequences could be severe. First, consider our satellites. These orbiting instruments are designed to withstand solar flares, cosmic rays, and occasional gamma bursts. But a Magnetar flare, the kind released in SGR 1806-20's 2004 giant flare, is orders of magnitude stronger. Gamma rays and high-energy particles could fry sensitive electronics, disrupting GPS systems, weather satellites, and communication networks around the globe. Space agencies like NASA and ESA continuously monitor high-energy events, precisely because even minor disruptions in satellite functionality can cascade into widespread technological problems on Earth. Next, there's the atmosphere itself. Gamma rays from a nearby Magnetar flare could ionize the upper atmosphere, creating temporary but significant disturbances. Layers like the ionosphere, which normally shield us from cosmic radiation, would absorb a flood of high-energy particles, alter radio wave propagation, and potentially leading to global communication blackouts. In extreme scenarios, these bursts could even deplete protective layers like ozone in localized regions, allowing harmful ultraviolet radiation to penetrate the surface. Even life itself could be at risk if a magnetar flare were close enough. Gamma rays and X-rays carry enough energy to damage DNA and disrupt biological processes, while the likelihood of direct extinction level events is low given the distances of known magnetars. Studies suggest that past mass extinctions might, in part, reflect exposure to intense cosmic radiation from events such as nearby supernovae or magnetar flares. Fortunately, no known magnetar exists close enough to Earth to pose an immediate threat. The nearest confirmed magnetars are thousands of light-years away, and their giant flares are not aimed at our planet, yet the possibility remains. The existence of these cosmic monsters reminds us of the raw power lurking in our galaxy, objects that are capable of releasing energy on a scale that dwarfs human imagination. They are living examples of how fragile our technological civilization, and indeed life itself, would be if a truly extreme event occurred nearby. In short, magnetars are not just distant curiosities, they are galactic wildcards, forces of nature whose presence highlights both the danger and the wonder of the universe. For a fraction of a second, they can affect space, matter, and energy across thousands of light-years and even touch our world from afar. In the vast darkness of space, astronomers have been detecting a mystery for over a decade: fast radio bursts, or FRBs. These are extremely brief flashes of radio waves, lasting only a few milliseconds, yet releasing as much energy as the sun emits in an entire day. They appeared suddenly from distant galaxies, and then disappeared without a trace. Their origins were unknown. Were they colliding with neutron stars, supernova remnants, or something far stranger, hiding in the cosmic shadows? For years, these FRBs teased scientists, arriving sporadically and unpredictably, challenging every model of high-energy astrophysics. The universe was speaking in a language that we could not yet fully decipher. Then, in 2020, a breakthrough occurred. A magnetar inside our own galaxy, SGR 1935 plus 2154, produced an FRB-like event. Unlike previous detections from billions of light years away, this one was close enough to be studied in detail. It emitted a radio burst that matched the energy and time profile of extragalactic FRBs, bridging the gap between theory and observation. This event was monumental. For the first time, scientists had a tangible link between magnetars, objects we already knew to be extreme, unpredictable and violent, and the mysterious fast radio burst that had puzzled astronomers for years. The connection suggested that at least some FRBs are generated by magnetars. The magnetic stress, starquakes, or sudden rearrangements of the magnetic field could accelerate electrons, producing radio waves that travel across the universe at nearly the speed of light, eventually reaching our telescopes. The implications were profound. Magnetars were no longer just isolated cosmic monsters. They became potential cosmic messengers, sending bursts of information across millions or even billions of light years. Every FRB detected could now represent a magnetar's dramatic outburst, a star flaring in pain, or a quantum-scale event that reverberates across the galaxy. Suddenly, these distant, mysterious flashes were no longer random. They were part of a story we could begin to read, connecting the violent physics of magnetars to observable phenomena in the cosmos. In other words, magnetars not only challenge the limits of matter, energy and magnetism, they also communicate across the universe, hinting at processes so extreme that they were once considered impossible. With SGR 1935 plus 2154, the decade-long mystery of FRBs now had a plausible explanation. Yet it also opened a new set of questions. How many magnetars produce FRBs? What triggers each burst? And how does the structure of a magnetar's magnetic field shape the signal we detect across light years? The universe had given us a glimpse into its hidden language, and magnetars were the authors. These city-sized, ultramagnetic stars were no longer just objects of fear. They were keys to understanding some of the universe's most profound and energetic mysteries. Every FRB is now a clue, a cosmic telegram sent from a magnetar somewhere in the depths of space, telling a story that only now we are learning to interpret. When most people think of extreme objects in the universe, their minds jump immediately into black holes. These cosmic titans are often described as the ultimate monsters of space, swallowing everything that comes too close, hiding their secrets behind the inescapable event horizon. They are mysterious, dangerous, and seemingly beyond comprehension, a point where our understanding of physics collapses under the weight of gravity. Yet, despite all their notoriety, black holes are not the only cosmic oddities that push the boundaries of physics. Magnetars in many ways challenge everything we thought we knew about the limits of matter, energy, and magnetic phenomena. Unlike black holes, a magnetar does not hide behind a veil. Its interior is not invisible. Its fury is observable, measurable, and testable. Every outburst, every magnetic flare, every X-ray pulse provides scientists with real-time laboratories of extreme physics, opportunities to witness conditions that cannot be recreated anywhere on Earth. At their cores, magnetars are a collision of physical extremes. Gravity is intense, packing more mass than the Sun into a sphere barely 20 kilometers across. Magnetism dominates, reaching strengths of 10 to the 15th power, Gauss trillions of times more powerful than Earth's field. And quantum physics becomes visible as vacuum birefringence bends light, starquakes release energies that dwarf any explosion on Earth, and the interactions of subatomic particles are forced into states that defy everyday intuition. These are places where different laws of physics converge, and sometimes appear to contradict one another, offering scientists a glimpse of nature's deepest secrets. In a sense, magnetars are nature's ultimate experiment. Unlike a black hole, which hides all its inner workings behind a one-way boundary, a magnetar allows physicists to watch extreme forces in action. We can measure the magnetic field directly through cyclotron lines in X-ray spectra. We can witness crustal fractures as starquakes produce gamma-ray bursts. we can see quantum electrodynamics in action, with light splitting and bending in ways that confirm theory or challenge it. Magnetars do not destroy the universe, they reveal it. They are proof that our understanding of reality is incomplete, that the cosmos contains objects so extreme, so fundamentally alien, that they redefine what we consider possible. Gravity, magnetism, and quantum mechanics collide here in ways we're only beginning to comprehend. And in their fury, Magnetars remind us of the ultimate truth. The universe is far stranger than we ever imagined, and sometimes the most violent objects are also the most illuminating. Magnetic decay in magnetars is not a simple weakening process. It is a complex transformation of magnetic energy into heat and radiation over time. Inside the star, the magnetic field is anchored in an ultra-dense electrically conducting medium. Because of this, the field does not simply fade away smoothly. Instead, it evolves through processes such as ohmic decay, Hall drift, and ambipolar diffusion. Ohmic decay occurs due to the finite electrical resistance in the crust, slowly dissipating magnetic energy as heat. Hall drift, on the other hand, redistributes magnetic energy within the crust without directly losing it, often concentrating it into smaller regions where it can later be released more violently. Ambipolar diffusion takes place deeper in the core, where charged particles and neutrons move together under magnetic stress, gradually transporting energy outward. These combined processes create a continuous internal heating system. Unlike ordinary neutron stars that cool steadily after formation, magnetars can remain thermally active for tens of thousands of years. Their surface temperatures, often exceeding 1,000,000 degrees Kelvin, are sustained not by nuclear fusion, but by the slow release of magnetic energy. This makes them unique among stellar remnants, as their brightness is powered by magnetism rather than rotation, or residual heat alone. The magnetosphere of a magnetar is not just a passive region filled with trapped particles. It is an active and evolving structure shaped by extreme magnetic stress. In normal neutron stars, magnetic field lines are relatively stable and dipolar. In magnetars, however, these field lines become globally twisted, forming what scientists call a twisted magnetosphere. This twist is crucial because it stores enormous amounts of energy. The field lines behave like tightly wound springs. As the internal magnetic field evolves, it pushes outward, twisting the external field. This twist supports strong electric currents flowing through the magnetosphere, which in turn produce persistent X-ray emissions. Over time, the twist becomes unstable. When it reaches a critical point, the field lines can suddenly snap back into a lower energy configuration. This process releases energy in the form of radiation and accelerated particles, similar to solar flares but vastly more powerful. These events are responsible for many of the bursts and flares observed by magnetars. Additionally, the magnetosphere is filled with dense plasma, much denser than in typical pulsars. This plasma affects how radiation escapes, often scattering and modifying the light before it reaches observers. As a result, what we detect from Earth carries the imprint of these extreme magnetic environments. The rotational behaviour of magnetars provides a rare window into their internal structure. Inside the star, beneath the rigid crust, lies a superfluid core made primarily of neutrons. This superfluid has zero viscosity, meaning it can flow without resistance and store angular momentum independently of the crust. In a glitch event, angular momentum is suddenly transferred from the faster spinning superfluid interior to the crust, causing the star's rotation to speed up slightly. This suggests that the interior and exterior are not perfectly coupled. They can move somewhat independently. Anti-glitches, which are much rarer, are even more mysterious. These involve a sudden decrease in rotational speed and are thought to be linked to external magnetic processes rather than internal ones. For example, a sudden reconfiguration of the magnetosphere could apply a braking torque to the star, slowing it down abruptly. These events are extremely important because they provide indirect evidence of conditions deep inside the magnetar. Since we cannot observe the interior directly, changes in rotation act like signals, revealing how matter behaves under extreme density. superfluidity and magnetic stress. The magnetic field of a magnetar is highly complex, extending far beyond a simple north-south dipole structure. Near the surface, higher-order components such as quadrupole and octupole fields dominate. These create localized regions of extremely intense magnetic stress. This complexity leads to what can be described as an energy cascade. Large-scale magnetic structures gradually transfer energy into smaller, more concentrated regions. These regions become hotspots for activity, where stress builds up until it is suddenly released. This process is similar to turbulence in fluids, where energy moves from large motions to smaller ones until it dissipates. In magnetars, this cascade determines where and how bursts occur. It also explains why some magnetars show repeated activity in specific magnetic on their surface. Understanding this geometry is essential for predicting magnetar behavior. It also connects to broader physics, as similar cascade processes are studied in plasma physics, fluid dynamics, and even atmospheric science. The crust of a magnetar is one of the most extreme solid structures known. At densities just below the core, atomic nuclei are so compressed that they begin to merge into unusual configurations collectively known as nuclear pasta. These structures form because of competing forces. The strong nuclear force tries to hold matter together, while electrostatic forces push it apart. The result is matter arranged in shapes resembling sheets, lasagna, rods, spaghetti, and more complex forms. This exotic structure gives the crust incredible strength, making it billions of times stronger than steel. However, this strength also means that when it fails, it does so catastrophically. Instead of small cracks, the crust can fracture on a large scale, releasing immense energy. These properties are critical for understanding starquakes. The rigidity of the crust allows stress to build up over long periods, while its eventual failure triggers sudden and powerful energy releases. Studying this material helps physicists explore how matter behaves at nuclear densities, something impossible to replicate in laboratories. Neutrinos play a silent but crucial role in the life of a magnetar. In the early stages after formation, the star cools rapidly by emitting neutrinos from its dense core. These particles interact so weakly with matter that they escape almost instantly, carrying away energy. Even later in the magnetar's life, neutrino emission continues to influence its thermal balance. While magnetic decay heats the star, neutrino processes work in the opposite direction, cooling it. The competition between these two processes determines the star's temperature over time. Different cooling mechanisms can operate depending on the internal composition, such as the direct Urca process, which allows rapid neutrino emission if certain conditions are met. Observing how magnetars cool provides indirect evidence about their internal structure, including whether exotic particles or phases of matter exist in their cores. Magnetars are capable of accelerating particles to extremely high energies through magnetic reconnection and electric fields in their magnetospheres. When magnetic field lines snap and reconnect, they release energy that accelerates charged particles such as electrons and protons to near-light speeds. These particles can escape into space, contributing to the population of cosmic rays that travel across the galaxy. In some cases, the energy involved is so high that they approach the upper limits observed in cosmic ray experiments on Earth. This makes magnetars potential contributors to the most energetic particles in the universe. Their role in cosmic ray production is still being studied, but it highlights how these objects are not isolated phenomena. They actively influence the broader galactic environment. Although rare, magnetars in binary systems could produce some of the most unusual astrophysical phenomena. The intense magnetic field can interact directly with a companion star, stripping away material or altering its outer layers. If the companion falls toward the magnetar, it can interact with the magnetic field in complex ways, producing additional radiation or triggering bursts. These systems could also help explain certain unusual X-ray sources observed in the galaxy. Beyond binary systems, magnetars also shape their surrounding environment. Their magnetic winds and radiation can heat nearby gas, influence star formation, and create nebulae powered by magnetic energy rather than traditional processes. When a magnetar experiences a starquake, the sudden shift in its structure can cause the entire star to oscillate. These oscillations, known as torsional modes, involve twisting motions of the crust and can last for several seconds. If these vibrations are not perfectly symmetrical, they can produce gravitational waves, ripples in space-time that travel outward at the speed of light. While current detectors may struggle to detect such weak signals, future advancements could make it possible. Detecting gravitational waves from magnetars would provide a completely new way to study their internal structure, offering direct evidence of how matter behaves under extreme conditions. Magnetars push magnetic fields to the edge of what physics allows. At extremely high strengths, new quantum effects become important. For example, there is a theoretical limit known as the quantum critical field, beyond which the vacuum itself becomes unstable to particle creation. Magnetars operate near or above this threshold, meaning their magnetic fields can influence not just matter, but the very structure of space. Studying them helps test the limits of quantum electrodynamics under extreme conditions. If even stronger fields were discovered, it could indicate new physics beyond current theories. In this way, magnetars act as natural experiments, probing the boundaries of what is physically possible. The question may sound like the stuff of science fiction, but it is grounded in real science. Magnetars are among the most energetic objects in the universe, capable of releasing in a fraction of a second more energy than the Sun produces in 100,000 years. And while they are rare, their potential impact on a nearby planet is profound. If a magnetar were located within about 10,000 light-years of Earth and unleashed a giant flare directly in our direction, the consequences could be catastrophic. Satellites in orbit could be instantly damaged or destroyed, crippling communications, GPS systems, and even weather forecasting. Power grids on the surface could be fried, similar to the effects of a massive solar storm but magnified by the sheer intensity of gamma radiation. Even Earth's atmosphere would not remain untouched. The ionosphere could be ionized, altering atmospheric chemistry and increasing the risk of ultraviolet radiation reaching the surface. Fortunately, the cosmos has spared us so far. None of the known magnetars are close enough to pose an immediate threat. The closest active magnetar, as catalogued by astronomers, is still tens of thousands of light-years away, a distance that renders its bursts harmless to life on Earth. Yet the possibility exists. Somewhere, hidden in the galaxy, a magnetar could be quietly building up magnetic tension, waiting for the moment to release energy in a flare so powerful that the effects would ripple across light years. This possibility is not meant to incite fear, but to remind us of a humble truth. The universe is not designed with human safety in mind. Cosmic catastrophes are not intentional. They are the natural consequences of extreme physics at work. Life on Earth exists in a delicate balance, protected from most of these cosmic hazards by distance, luck, and the laws of space. But the potential for destruction serves as a stark reminder of just how powerful, strange, and unpredictable the universe truly is. Magnetars are not malevolent, they are indifferent, and their existence proves that the cosmos contains forces far beyond our control or comprehension. Even after decades of observation and study, magnetars remain among the most enigmatic objects in the universe. Astronomers and physicists continue to wrestle with fundamental questions about their nature. For instance, how are their unbelievably powerful magnetic fields generated? While theories point to rapid rotation and convective dynamos during the birth of a neutron star, the exact mechanisms are still under investigation. Another puzzle lies in rarity. Only a small fraction of neutron stars evolves into magnetars. What subtle differences in mass, rotation, or internal composition determine which stars become these cosmic monsters? Even more perplexing are the triggers for their most violent outbursts. Some flares occur seemingly without warning, releasing energy equivalent to 1 billion nuclear bombs in fractions of a second. Scientists are still trying to understand how stress in the crust, magnetic instabilities and quantum effects combine to produce these hyperflares. Additionally, magnetars do not exist in isolation. Their intense magnetic fields interact with the surrounding interstellar environment, influencing particle acceleration, radiation, and even the formation of fast radio bursts. Every new observation adds a piece to this cosmic puzzle. X-ray telescopes like Chandra and NuSTAR, radio arrays such as CHIME, and space missions like SWIFT continually provide data that challenge and refine our understanding. Yet for all we have learned, the full picture remains incomplete. Magnetars are living laboratories of extreme physics, offering a glimpse into phenomena that cannot be reproduced on Earth. They remind us that the universe is not only stranger than we imagine, but often stranger than we can imagine. Even as we gaze at the night sky, calm and serene from Earth, the truth is far more dramatic. Somewhere in our galaxy, a Magnetar is alive and active, a city-sized remnant of a star long dead, yet brimming with untamed energy. Its magnetic field twists the very fabric of space, stretching atoms, bending light, and creating conditions that push the laws of physics to their limits. Deep within its crust, stress accumulates from the interplay of gravity and magnetism, building energy that can erupt without warning. At any moment, this compact powerhouse could release a flare so intense that it would be detectable across the galaxy, a violent heartbeat echoing across tens of thousands of light years. The universe is not calm, it is not orderly, it is not a place where everything behaves as expected. Magnetars demonstrate this in ways that challenge our most established theories. Unlike black holes, which hide their extremes behind event horizons, magnetars expose everything: gravity, magnetism, and quantum effects all laid bare. They are laboratories of cosmic extremes, testing the boundaries of matter, energy, and space itself. And yet, despite their power, they are small, barely 20 kilometers across, reminding us that scale is relative, and danger does not always come in the largest packages. These dead stars, these magnetars, are rewriting the rules of the cosmos. They push the universe to reveal its most hidden extremes, showing us that our understanding is still limited. What we see in the night sky is only the surface. Beneath it, forces operate that defy intuition, break physics, and challenge imagination. They are a warning and a marvel. The universe is far stranger and more violent than we thought, and the next burst, the next scream from a magnetar could occur at any moment. Somewhere out there, a dead star waits, quietly bending reality, reminding us that even in the vastness of space, the most extreme phenomena are often the ones we least expect. Picture two Magnetars, born from separate supernovae, hurtling through the galaxy like silent predators. For eons they drift independently, their magnetic fury contained. But gravity, that relentless architect of chaos, eventually draws them into a fatal dance. As they spiral closer, their colossal fields begin to tangle, twisting into a monstrous knot of energy. Space itself screams as field lines snap and reconnect, unleashing flares brighter than 1 trillion suns. This is no ordinary merger. Unlike neutron-star collisions that birth kilonovae and gold, magnetar duos amplify the apocalypse. Simulations show their combined fields could generate gravitational waves laced with unprecedented gamma bursts, rippling across the cosmos. The energy? Enough to sterilize star systems for light years, vaporizing atmospheres and igniting plasma storms. If one occurred in a nearby galaxy arm, we'd witness the sky ignite a cosmic fireworks display of annihilation. Yet from destruction springs revelation. Detectors like LIGO might catch the ripples, decoding the final throes of these beasts. Astronomers predict such events explain some ultra-long gamma-ray bursts, remnants of magnetars devouring each other in the universe's most violent embrace. These collisions aren't just ends, They're beginnings of new mysteries proving even cosmic monsters can't escape their own power. Now, imagine approaching a Magnetar, not from millions of kilometers away, but close enough that gravity is no longer the greatest threat. At this proximity, an entirely different force dominates magnetism so intensely it warps reality itself. The surface of the Magnetar defies all familiar states of matter. It is not liquid, not gas, and not solid in any sense we can relate to. Scientists believe the outer shell is a crystalline lattice of iron, compressed so densely that it acts as a single unbroken structure, stronger than any material humanity has ever forged. Here, cracks do not form, molecules cannot move. Chemistry as we know it ceases to exist. Beneath this extraordinary crust lies something even strange, a superfluid sea of neutrons. Not atoms, not molecules, just neutrons packed to densities so extreme they behave collectively as a frictionless fluid, flowing effortlessly through the depths of the star. In this realm, classical physics begins to lose meaning. Forces that govern the matter around us on Earth behave entirely differently. Electron clouds elongate into needle-like shapes under the star's magnetic field, and atoms themselves are twisted and stretched beyond recognition. And deeper still, where density approaches nuclear limits, even our best theories strain under pressure. The interplay of gravity, nuclear forces, and magnetism creates conditions that are almost impossible to simulate in any laboratory. Matter behaves in ways that almost alien forces combine, warp, and sometimes contradict the principles we think are universal. Inside a Magnetar, the universe presents a world beyond matter, a realm where the very rules of physics are stretched, bent, and sometimes shattered, offering a glimpse into the extremes of reality that exist nowhere else in the cosmos. Humanity's telescopes stand as silent sentinels, piercing the cosmic veil to track these ticking time bombs. NASA's Chandra X-ray Observatory locks onto their searing gamma flares with unmatched precision, mapping magnetic field twists down to 0.1% accuracy across 50,000 light-years. The James Webb Space Telescope, JWST, peers through infrared dust clouds, revealing newborn magnetars still shedding supernova debris, their fields pulsing every 2 to 10 seconds, like erratic heartbeats. Europe's integral satellite catches high-energy bursts in real time, triangulating positions within minutes using gamma-ray interferometry. Then came the game-changer. 2025 observations of a flaring magnetar in M31, the Andromeda Galaxy, just 2.5 million light-years away. ESA's XMM Newton and New Star caught it mid-Starquake crust fracturing under 10 to the 15th power Gauss pressures, decaying 15% faster than models predicted. Real-time spectra showed cyclotron lines shifting from 5 kilo-electron-volts to 3 kilo-electron-volts in weeks, proving magnetic reconnection accelerates field erosion. Alerts flashed across NASA's Fermi GBM network and Russia's Conus Wind, pinging global arrays like LIGO/Virgo for gravitational precursors. Within hours, astronomers worldwide recalibrated orbits, shielding satellites from the inbound X-ray storm. These aren't passive watches. Knowledge forges our shield. Swift's Burst Alert telescope now auto-adjusts orbits for 30+ known magnetars, hardening electronics against gamma doses up to 10 to the 8th erg per square centimetre, enough to fry unshielded GPS birds. ESA's Space Weather Office models ionospheric disruptions, predicting blackouts 24 to 48 hours ahead via solar wind proxies. Ground stations from Mauna Kea's Subaru to Chile's VLT deploy Faraday cages, while SpaceX's Starlink constellation tests Faraday fabrics, slashing flare-induced downtime by 70%. By decoding Magnetar's cyclotron whispers and quake tremors, we fortify satellites, predict blackouts, and harden power grids against induced currents, rivaling 1859's Carrington event. They aren't mere threats, they're unrelenting teachers, forcing humanity to evolve. In their millisecond pulses SGR 1806-20's 7.5 Hz spin, 2020's FRB linked SGR 1935 + 2154, we hear the universe's raw heartbeat, wild, unforgiving, infinitely wondrous. One day, their roar might demand we answer. Photon splitting is one of the rarest quantum processes observed in extreme astrophysical environments. Under normal conditions, a photon, which is a particle of light, cannot simply divide into two separate photons. This would violate the usual rules of quantum electrodynamics. However, near a magnetar, the magnetic field is so extraordinarily strong that it changes the behaviour of the vacuum itself, allowing this forbidden process to occur. In such an intense magnetic environment, a high-energy gamma-ray photon can split into two lower-energy photons without interacting with matter. This happens because the magnetic field provides the necessary conditions for energy and momentum to be conserved during the process. The field essentially acts as a mediator, making the impossible possible. This phenomenon has a major impact on what astronomers observe. Instead of detecting strong gamma-ray emissions directly, many of these high-energy photons are converted into X-rays before they escape the magnetar surroundings. As a result, the radiation spectrum appears softer than expected. This suppression of high-energy photons explains why magnetars often show unusually strong X-ray emissions compared to gamma rays. Beyond observation, photon splitting also changes how energy moves through the magnetar's environment. Energy that would normally escape quickly as high-energy radiation is redistributed into lower-energy forms. This slows down the escape of energy and creates a more complex radiation pattern, making magnetars far more difficult to model accurately. Resonant cyclotron scattering is a key process that shapes the radiation we detect from magnetars. In the magnetosphere, electrons are not free to move in a simple way. Instead, they are tightly bound to magnetic field lines and forced to spiral around them at specific frequencies known as cyclotron frequencies. When photons pass through this region, they can interact with these spiraling electrons. If the energy of the photon matches the natural frequency of the electron's motion, a resonance occurs. At this point, the photon can exchange energy with the electron very efficiently. It may gain energy, lose energy, or change direction entirely. This interaction significantly modifies the radiation before it escapes into space. Light emitted from the surface does not travel directly outward in a straight and unchanged path. Instead, it is repeatedly scattered, reshaped, and redistributed by the magnetosphere. This is why magnetar spectra often contain features that cannot be explained by simple surface emission alone. Understanding resonant cyclotron scattering is essential for interpreting observational data. Without accounting for this process, scientists would misinterpret the temperature, composition, and magnetic field strength of the magnetar. It essentially acts as a filter that reshapes the star's true signal. Even when magnetars are not producing dramatic bursts or flares, they remain extremely bright in X-rays. This steady emission is known as persistent X-ray radiation, and it is one of their defining characteristics. Unlike normal neutron stars, which cool steadily over time, magnetars maintain high temperatures due to continuous magnetic energy release. This emission is not evenly spread across the surface. Instead, it originates from localized regions called hotspots. These hotspots form because magnetic field lines are not uniformly distributed. Twisted and concentrated magnetic regions channel energy back towards specific niket on the surface, heating them far more than surrounding areas. As the magnetar rotates, these hotspots move in and out of view, causing periodic variations in brightness. By carefully studying these variations, scientists can map the surface temperature distribution. This technique allows researchers to indirectly study the structure of the magnetic field and understand how energy flows from the interior to the surface. Hotspots also evolve over time. Their size, temperature, and position can change as the magnetic field rearranges itself. This makes them valuable indicators of the Magnetar's internal activity and long-term evolution. Magnetars are not only sources of radiation, they also emit powerful streams of particles known as magnetar winds. These outflows consist mainly of highly energetic electrons and positrons that are accelerated by the star's magnetic field. Unlike the solar wind, which is driven by heat and pressure, magnetar winds are driven primarily by magnetic forces. The intense magnetic field transfers energy to charged particles, pushing them outward at extremely high speeds. These winds can carry a significant amount of energy away from the star. As these particles move into surrounding space, they interact with interstellar material, creating shock waves and regions of high energy emission. In some cases, this leads to the formation of extended nebulae around the magnetar. These structures glow in X-rays and radio waves, providing visible evidence of the magnetar's influence beyond its immediate surface. These winds also play a role in redistributing energy within the galaxy. Even though magnetars are small, their winds can affect regions many times larger than the star itself, showing how powerful their influence truly is. After the supernova explosion that forms a magnetar, not all material is successfully ejected into space. Some of it may fall back toward the newly formed neutron star, forming a structure known as a fallback disk. These disks are usually faint and difficult to detect, but they can have important effects on the magnetar's behaviour. The interaction between the disk and the magnetic field can influence the star's rotation. In some cases, it may slow down the magnetar or create additional torque that changes its spin over time. Fallback disks may also contribute to low-level emissions. As material in the disk interacts with the magnetic field, it can heat up and produce radiation. This adds another component to the already complex emission profile of magnetars. Although not all magnetars are confirmed to have fallback disks, their possible presence suggests that some magnetars are not completely isolated systems. Instead, they may still be interacting with remnants of their own formation. Magnetic reconnection is a process where magnetic field lines break and reconnect, releasing stored energy. While this process occurs in many places, such as the Sun, it reaches extreme levels in magnetars. In a magnetar, the magnetic field is so strong and twisted that it stores enormous amounts of energy. When reconnection occurs, this energy is released almost instantly. This is one of the main mechanisms behind magnetar flares and bursts. The scale of these events is far beyond anything observed in the solar system. The energy released can accelerate particles to near-light speeds and produce intense gamma-ray radiation. Despite its importance, the exact physics of reconnection under such extreme conditions is not fully understood. Studying magnetars allows scientists to test theories of plasma physics in environments that cannot be recreated on Earth. This helps improve our understanding of how magnetic fields behave in extreme situations across the universe. Magnetars do not rotate with perfect regularity. Instead, they show small but noticeable variations in their rotation, known as timing noise. These irregularities are linked to internal and magnetic processes within the star. Unlike stable pulsars, which act like precise cosmic clocks, magnetars are more unpredictable. Their rotation can change due to crust fractures, magnetic stress, or interactions between the crust and the superfluid interior. Each variation provides valuable information. By studying these timing changes, scientists can infer what is happening inside the magnetar. It is one of the few ways to probe the internal structure of such an extreme object. Although this makes magnetars less useful for precise timing applications, it makes them far more interesting from a physical perspective, as they reveal dynamic internal processes. During powerful flares, magnetars may produce not only light, but also high-energy neutrinos. These particles are extremely difficult to detect because they interact very weakly with matter. Neutrinos are created when high-energy particles collide with radiation or surrounding material. In the extreme environment of a magnetar, such interactions can produce neutrinos with enormous energies. What makes neutrinos important is that they travel through space almost unaffected. Unlike light, they are not absorbed or scattered easily. This means they carry direct information from the source. If detected, neutrinos from magnetars would provide a completely new way of studying these objects. They would allow scientists to observe processes that are otherwise hidden, making magnetars part of what is known as multi-messenger astronomy. Magnetars contribute to the galaxy in subtle but meaningful ways. Their radiation and particle emissions can alter the physical and chemical state of nearby interstellar material. High-energy radiation from magnetars can ionize gas clouds, changing how atoms and molecules behave. This can influence chemical reactions and affect how new stars form in those regions. Although magnetars are not the main source of heavy elements, their energy output can still shape the environment where these elements exist. Over long periods, this contributes to the overall evolution of the galaxy. This highlights that magnetars are not isolated phenomena. They are active participants in the larger cosmic system, influencing their surroundings in ways that extend far beyond their size. One of the most important observational features of magnetars is the strong polarization of their emitted light. Polarization means that the light waves are aligned in a specific direction rather than being random. This happens because the magnetic field strongly influences how photons move through space. As light travels through the magnetar's environment, it interacts with the magnetic field in a way that forces it into specific polarization states. Measuring this polarization provides direct evidence of extreme physical effects such as vacuum birefringence. It allows scientists to test advanced theories of quantum physics in real astrophysical conditions. Polarization studies also help map the structure of the magnetic field. By analyzing how light is polarized, researchers can infer the geometry and strength of the field, giving deeper insight into how magnetars operate. In the environment of a magnetar, the magnetic field is so intense that it significantly alters the behavior of the quantum vacuum itself. In quantum electrodynamics, the vacuum is not empty, but consists of constantly fluctuating virtual particle-antiparticle pairs. Under normal conditions, these fluctuations cancel out on average and have negligible observable effects. However, when exposed to magnetic fields approaching or exceeding the quantum critical limit, around 1013 to 1015 Gauss, the vacuum becomes polarized. This polarization means that virtual particles align in response to the magnetic field, causing the vacuum to behave like a physical medium rather than empty space. As light propagates through this region, its speed and polarization are affected depending on its orientation relative to the magnetic field. This leads to vacuum birefringence, where a single light wave splits into two distinct polarization modes traveling at slightly different velocities. These effects are extremely subtle, but measurable in principle through polarization studies of X-rays emitted by magnetars. This phenomenon is one of the strongest confirmations of quantum field theory predictions in astrophysical settings. It demonstrates that space itself can behave like a medium under extreme conditions, bridging the gap between classical optics and quantum physics. Near a magnetar, high-energy photons interacting with the strong magnetic field can transform directly into matter in the form of electron-positron pairs. This process does not require interaction with another particle, because the magnetic field provides the necessary conditions to conserve momentum and energy. Once a photon converts into a pair, the resulting electrons and positrons are accelerated along magnetic field lines. As they move, they emit additional high-energy photons through processes such as curvature radiation and synchrotron radiation. These secondary photons can then produce more particle pairs, leading to a cascading chain reaction. This cascade rapidly fills the magnetosphere with a dense relativistic plasma composed of electrons and positrons. The presence of this plasma is essential for sustaining magnetospheric currents and for enabling further radiation processes. Without pair production cascades, the magnetosphere would not maintain the high particle densities required to support observed emission mechanisms. The cascade also regulates the magnetosphere. If particle density becomes too low, electric fields build up and accelerate particles until pair production resumes, restoring equilibrium. This self-regulating system is a key feature of Magnetar environments. Magnetar-magnetic fields are rarely simple and static. Instead, they often develop complex twisted structures due to internal motion within the star's crust and core. These twists introduce toroidal components to the otherwise primarily dipolar magnetic field, creating a more complicated three-dimensional topology. A twisted magnetic field stores additional energy compared to a relaxed dipole configuration. This stored energy is associated with currents flowing along the field lines, which maintain the twist. These currents are responsible for heating the surface at specific regions where the field lines connect, producing localized hotspots. Over time, the twist can increase due to internal stresses or decreases through magnetic reconnection and radiative losses. When the twist becomes too large, the system becomes unstable and may partially unwind, releasing energy in the form of bursts or flares. This dynamic evolution of the magnetic field topology is directly linked to the variability observed in Magnetar emissions, including changes in brightness, spectrum, and activity levels. Inside a magnetar, matter exists under extreme densities, where the core is believed to contain superfluid neutrons and superconducting protons. In a superfluid state, particles flow without viscosity, allowing them to move independently of the crust under certain conditions. The crust, being a rigid lattice of nuclei, rotates as a solid structure. However, it is coupled to the superfluid interior through quantized vortex lines that carry angular momentum. These vortices can become pinned to the crust, temporarily locking the rotation of the superfluid to that of the crust. When stresses build up, these vortices can suddenly unpin and transfer angular momentum to the crust, resulting in a sudden change in rotation known as a glitch. This interaction between the crust and the superfluid interior is complex and not fully understood, but it provides a mechanism for internal energy and angular momentum redistribution. The coupling also plays a role in how energy from the interior is transported outward, influencing both thermal evolution and rotational behavior. Studying these processes offers insight into the physics of matter at nuclear densities, which cannot be replicated in laboratory conditions. Magnetar bursts occur when the system reaches a critical threshold of magnetic stress or structural instability. As magnetic field lines evolve and twist, they exert forces on the crust, gradually increasing internal stress. When this stress exceeds the elastic or plastic limit of the crust, a sudden fracture or deformation occurs. This event can rapidly reconfigure the magnetic field, leading to the release of stored magnetic energy. The energy release may also trigger magnetic reconnection events in the magnetosphere, amplifying the burst. The triggering mechanism is not uniform and may involve a combination of crust cracking, magnetic instability, and plasma interactions. The threshold behavior explains why magnetars can remain inactive for long periods and then suddenly produce intense bursts. It also suggests that the internal state of the magnetar is constantly evolving toward instability until a release event resets the system partially. The spectrum of radiation emitted by a magnetar is not fixed, but changes depending on its activity state. During periods of increased magnetospheric activity, the emitted radiation tends to shift toward higher energies, a phenomenon known as spectral hardening. This is typically associated with increased particle acceleration, stronger currents, and enhanced scattering processes. During quieter periods, the spectrum shifts toward lower energies, or spectral softening, as particle densities decrease and scattering becomes less efficient. These spectral changes reflect the underlying physical conditions of the magnetosphere, including temperature distribution, plasma density, and magnetic field configuration. By tracking spectral evolution over time, scientists can infer changes in the magnetar's internal and external environment. This makes spectral analysis a powerful diagnostic tool for understanding how energy is generated, transported, and dissipated within the system. As a magnetar rotates, its emission is observed as pulses due to the presence of non-uniform surface brightness and anisotropic radiation. The resulting light curve or pulse profile represents how the observed intensity varies with rotation phase. These pulse profiles are influenced by several factors, including the distribution of hotspots, the geometry of the magnetic field, relativistic light bending near the star's surface, and the observer's viewing angle. General relativity plays a role by bending light paths, allowing observers to see regions that would otherwise be hidden. The resulting pulse shapes can be complex, often showing multiple peaks or asymmetries. These features encode information about the magnetar's geometry and emission mechanisms. By modelling these pulse profiles, scientists can reconstruct the orientation of the magnetic axis relative to the rotational axis and estimate the size and location of emitting regions. Although magnetar magnetic fields are often approximated as dipoles for simplicity, the actual field structure is likely much more complex. Higher-order multipole components such as quadrupoles and octupoles can contribute significantly to the overall magnetic configuration. These multipole components create localized regions of enhanced magnetic intensity on the surface. As a result, the magnetic field strength can vary significantly across different regions of the star. This variation leads to the formation of multiple hotspots and contributes to the complexity of observed emission patterns. The interaction between dipole and multipole components also affects how magnetic energy is stored and released. In regions where field lines converge or intersect, stress can accumulate more rapidly, making these areas more prone to bursts or flares. Understanding the full magnetic geometry is essential for accurately modelling magnetar behaviour. Magnetars, through their radiation and particle emissions, can influence the interstellar medium in their vicinity. Their intense X-ray and gamma-ray output can ionize surrounding gas, increasing its temperature and altering its chemical composition. In star-forming regions, this radiation can have both constructive and destructive effects. It may compress nearby gas clouds, potentially triggering gravitational collapse and star formation. Conversely, it can also heat and disperse gas, preventing collapse and inhibiting star formation. Although the spatial influence of a single magnetar is limited, over long time scales, these effects contribute to the evolution of the local galactic environment. This demonstrates that magnetars are not isolated objects but active participants in the broader astrophysical ecosystem. Magnetars are believed to represent an early and highly active phase in the life cycle of certain neutron stars. Over time, their magnetic fields decay due to processes such as ohmic dissipation, Hall drift, and amber polar diffusion. As the magnetic energy decreases, the level of activity also declines. During this evolution, bursts become less frequent, the surface cools, and magnetospheric currents weaken. The magnetar gradually transitions into a more typical neutron star with lower magnetic activity and weaker emissions. This quiescent state may resemble that of ordinary pulsars, although the underlying magnetic history remains different. The timescale for this transition is relatively short on cosmic scales, typically tens of thousands to hundreds of thousands of years. This suggests that magnetars are transient phases rather than permanent states, providing a snapshot of neutron star evolution under extreme magnetic conditions. Detecting magnetars presents several challenges due to their observational characteristics. Many magnetars are identified only during periods of burst activity, when their emissions become bright enough to be detected by X-ray and gamma-ray observatories. In their quiescent state, their emissions are relatively faint and can be difficult to distinguish from other neutron stars. Interstellar absorption further complicates observations, as gas and dust between the magnetar and the observer can absorb or scatter high-energy photons. This reduces signal strength and can distort the observed spectrum. As a result, highly sensitive instruments and long observation times are often required to study these objects. Because of these limitations, the known population of magnetars is likely incomplete. There may be many more magnetars in the galaxy, that remain undetected due to inactivity or observational constraints. This introduces uncertainty in population estimates and suggests that Magnetars could be more common than currently observed. Magnetars may also help us understand something much larger than the origin of the universe. Right after the Big Bang, the universe was not calm or structured. It was extremely dense, incredibly hot, and filled with intense energy fields interacting in chaotic ways. Under those conditions, the laws of physics behave differently from how they do today. While we cannot recreate the exact environment of the early universe, Magnetars come remarkably close. Their dense structure, powerful magnetic fields, and extreme energy levels create conditions that are similar in some ways to those early moments. By studying Magnetars, scientists are able to observe how matter and energy behave under extreme pressure and magnetism. This provides valuable clues about how the universe may have evolved from its earlier state into the structured cosmos we see today. In this sense, Magnetars act like natural laboratories, helping us explore a time in the universe that would otherwise remain completely inaccessible. Magnetars are among the most powerful objects known, but they may not represent the absolute limit of what exists in the universe. Throughout the history of science, each time we believed we had discovered the most extreme phenomenon, something even more extraordinary was found. Black holes revealed limits of gravity. Magnetars revealed limits of magnetism and matter. This raises an important question. Could there be objects or phenomena even more extreme than Magnetars? Some theories suggest the possibility of exotic states of matter or unknown cosmic structures that go beyond our current understanding. While there is no clear evidence yet, the existence of Magnetars shows that the universe is capable of producing conditions far beyond what we once thought possible. They may not be the endpoint, but rather a step toward discovering something even more extraordinary. Gravity on a magnetar is not just intense, it is overwhelming, surpassing anything experienced on Earth or even near most stars. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time moves relative to an outside observer. On the surface of a magnetar, where mass is packed into a sphere barely 20 kilometers across, gravity is extreme, roughly 200 billion times stronger than Earth's. Under these conditions, time itself is stretched and slowed. For someone hypothetically stationed near a magnetar, seconds would pass more slowly compared to clocks on Earth. This effect is subtle compared to the dramatic time dilation near a black hole, but it is real and measurable. Even something as seemingly absolute as the passage of time becomes relative, highlighting how physics operates differently under extreme conditions. It is a stark reminder that reality is not uniform throughout the universe. On a magnetar, the flow of time bends, not metaphorically, but physically. Every tick of a clock there reflects the warping of space-time under gravity and the profound influence of a stellar corpse unlike any other. Neutron stars are already among the fastest spinning objects in the universe. Some of them rotate hundreds of times per second, whipping their dense mass around at incredible speeds. Magnetars, however, are a striking exception. Despite being more massive and denser than typical neutron stars, they spin comparatively slowly, completing one rotation every 2 to 10 seconds. That may seem leisurely, but consider the mass involved. Roughly 1.4 times that of our Sun compressed into a sphere barely 20 kilometers across. The rotational energy contained within that tiny volume is staggering, enough to power intense magnetic fields and catastrophic bursts when combined with other extreme forces. Each rotation of a magnetar sends beams of high-energy radiation sweeping across space like a cosmic lighthouse. If Earth happens to lie in the path of that beam, telescopes and detectors record regular pulses, creating the characteristic signals of pulsars in radio, X-ray or gamma-ray wavelengths. These pulses are often predictable, forming precise timing patterns that astronomers use to study the star's properties. But magnetars are fundamentally unstable. Their immense magnetic fields twist and stress their crust. occasionally causing glitches in their rotation. These sudden changes can alter the timing of pulses, sometimes slightly, sometimes dramatically, serving as a reminder that even the rotation of these dead stars is not entirely under their own control. Each irregularity provides scientists with crucial insight into the interior structure, magnetic stresses, and quantum behavior inside one of the universe's most extreme objects. Magnetars are far from isolated cosmic curiosities. After their violent birth in a supernova explosion, they often remain embedded within clouds of debris, expanding shells of gas, dust, and shock waves left behind by the star's death. This environment is already chaotic, but the presence of a magnetar transforms it into a stage for some of the most extreme astrophysical phenomena in the universe. The Magnetar's colossal magnetic field interacts with the surrounding material, twisting and accelerating charged particles to velocities approaching the speed of light. These accelerated particles emit intense radiation across the electromagnetic spectrum. From radio waves to X-rays and gamma rays, the result is a dynamic, high-energy environment where shock waves ripple outward, compressing nearby gas and heating it to millions of degrees. In some cases, these interactions give rise to magnetar-powered nebulae, glowing clouds of energized particles that shine far brighter than the remnants of the original supernova. These regions are far from calm. Unlike the relatively passive remnants of typical stellar explosions, a magnetar's neighborhood is continuously reshaped by its magnetic dominance. The interactions between the magnetar and its surroundings can create complex structures, trigger additional bursts of radiation, and even influence the formation of new stars in the vicinity. Each observation offers astronomers a window into the ongoing evolution of matter under extreme conditions, showing that a magnetar is not just a dead star, it is a cosmic engine, actively sculpting its local environment in ways that challenge our understanding of physics and stellar evolution. For decades, astronomers have been captivated and perplexed by sudden intense flashes of gamma radiation appearing across the cosmos. These events, known as gamma-ray bursts, are some of the most energetic phenomena ever observed, capable of releasing more energy in a few seconds than our Sun will emit over its entire 10 billion year lifetime. Their durations vary dramatically. Some last mere milliseconds, while others stretch for several seconds or more, leaving scientists scrambling for explanations. For a long time, the origins of these bursts were shrouded in mystery. Collapsing massive stars and merging neutron stars were considered likely culprits, but the discovery of magnetars introduced a new, compelling explanation, especially for the shorter, more erratic bursts. Magnetars, with their ultra-powerful magnetic fields and unstable crusts, can release enormous amounts of energy when these fields suddenly realign, or when the star's crust fractures in a catastrophic starquake. The resulting burst of gamma rays is focused, beamed across space, and can outshine entire galaxies for a fleeting moment. When a magnetar unleashes such a flare, the energy propagates across vast distances, travelling billions of light years before reaching our instruments. Despite the staggering scale, astronomers can detect these bursts and trace them back to their galactic origins. In effect, each gamma-ray burst becomes a cosmic signal, a brief but powerful message from a magnetar somewhere far across the universe. It is a stark reminder that these dead stars are not merely inert remnants, they are active, explosive engines capable of shaping and illuminating the farthest reaches of the cosmos. The notion of visiting a magnetar is, in almost every practical sense, impossible. Even the most advanced spacecraft humanity has designed would be obliterated long before reaching one. The magnetic fields surrounding a magnetar are so intense that they would scramble electronics, melt circuits, and distort atomic structures. No material we know of could withstand the tidal forces, the radiation, or the sheer energy released in a magnetar's vicinity. In effect, even approaching one would be fatal to any probe or person attempting the journey. Yet the imagination does not recognize these boundaries. If we could somehow observe a magnetar up close, we would witness a spectacle unlike anything on Earth. Matter would be stretched into unfamiliar shapes, atoms distorted by the magnetic intensity. Light itself would bend and split, revealing the bizarre quantum effects predicted by high-energy physics. Space would no longer feel empty. The vacuum around the star would shimmer and warp under the Magnetar's influence. Such a close encounter would offer a front-row seat to nature at its most extreme. Gravity, magnetism and quantum phenomena colliding with a single tiny object. While a visit is beyond our reach, the Magnetar continues to act as a natural laboratory for astronomers, giving us glimpses of physics that could never be replicated on Earth. In imagining it, we understand both our limitations and the extraordinary forces that govern the universe. Magnetars are far more than just distant stars. They are cosmic challenges to the very framework of human knowledge. Each observation forces scientists to confront the boundaries of physics, testing our theories in ways that no laboratory on Earth could replicate. The extraordinary densities, staggering magnetic fields, and extreme energies present conditions where classical physics and quantum mechanics intersect and sometimes clash. Despite decades of research, not everything a magnetar does fits neatly into our models. Some flares defy prediction, timing glitches occur without warning, and interactions with surrounding matter remain only partially understood. Each discovery exposes gaps in our understanding, reminding us that even the most well-established laws of nature have their limits. In this sense, magnetars are both teachers and mysteries. They sit at the very edge of known science, inviting us to observe, calculate and imagine but never fully predict. They're a vivid reminder that the universe is not a closed book, but an ongoing experiment, one that constantly challenges our perception of reality. Observing a magnetar is not just an astronomical pursuit, it is a journey to the frontier of human comprehension, where the known ends and the unknown begin. Even the most extreme objects in the cosmos cannot escape the passage of time. Magnetars, with their immense magnetic fields and violent outbursts, are no exception. Over thousands to tens of thousands of years, their magnetic fields gradually decay, releasing the enormous energy stored within them. As this field weakens, the dramatic flares, gamma-ray bursts and crustal quakes that once defined their activity begin to taper off. The star's violent tantrums grow less frequent, and the cosmic chaos surrounding it slowly diminishes. Eventually, the magnetar enters a quieter phase, losing the characteristics that made it so extraordinary. What remains is a neutron star still incredibly dense, still gravitationally extreme, and still a marvel of physics, but no longer a cosmic monster capable of reshaping reality around it. Its once dominant magnetic field, the force that stretched atoms, bent space, and torn apart from afar, fades into normalcy. The death of a magnetar is a slow, subtle transformation, a reminder that even in the universe, power is temporary, and every titan eventually yields to time. It is easy to dismiss magnetars as distant curiosities, objects so far away that their immense power could never reach us. After all, the Milky Way stretches over 100,000 light-years, and most known magnetars lie tens of thousands of light-years from Earth. But the galaxy is not static. It is vast, crowded, and constantly evolving. Rare, violent events do happen, and when they do, their reach can be staggering. A magnetar flare close enough to our planet within roughly 10,000 light-years could have serious consequences. Satellites could be fried by bursts of high-energy radiation, communication systems disrupted, and even the chemistry of Earth's upper atmosphere altered. While such an event is unlikely to wipe out life entirely, it could still create global disturbances, temporary blackouts, and significant technological challenges. This is a reminder that space is far from empty. It is active, unpredictable, and sometimes dangerous. The universe does not operate on a schedule convenient for humanity, and even distant stars can wield forces powerful enough to reach across light years. Magnetars, small in size but immense in power, are proof that cosmic threats are very real, even if we are lucky enough to remain largely untouched. You might wonder why scientists dedicate time and resources to studying objects so distant, so extreme, and seemingly disconnected from everyday life. The answer lies in the unique window they provide into the universe's most fundamental questions. Magnetars are natural laboratories, cosmic experiments conducted on scales we could never replicate on Earth. By observing them, we learn how matter behaves under pressures and densities far beyond anything on our planet. Their staggering magnetic fields offer clues about the evolution and limits of magnetism in the cosmos. They reveal the origins of the most powerful cosmic signals, from gamma-ray bursts to fast radio bursts, helping us trace the mechanisms behind phenomena that were once inexplicable. These dead stars, small in size yet enormous in power, exist scattered across the galaxy. Each one is a reminder that the universe operates according to laws both familiar and utterly alien. By studying magnetars, we expand our understanding of physics, pushing the boundaries of what we know and what we thought was possible. Magnetars do not only act on large but visible objects also. Their true impact begins at the smallest scales of existence. Under normal conditions, atoms have stable structures, with electrons orbiting nuclei in predictable patterns. Chemistry, biology, and even materials depend on this stability. However, near a magnetar, the magnetic field becomes so strong that it disrupts this balance completely. Electrons are forced into narrow, elongated paths, and atoms lose their natural shape. This means that the basic rules governing matter no longer behave in familiar ways. Substances that are stable on Earth would instantly fall apart or transform into something entirely different. Scientists are deeply interested in this because it allows them to study how matter behaves under extreme conditions. These observations may reveal new physical principles or hidden properties of particles that cannot be tested in laboratories on Earth. In this way, magnetars act as natural experiments, showing us how reality behaves when pushed far beyond normal limits. Light is one of the most reliable tools for understanding the universe, but magnetars show that even light is not immune to extreme conditions. Normally, light travels in straight lines, unless it is affected by gravity, or passes through materials like glass or water. Near a magnetar, however, the intense magnetic field changes how light moves through space itself. Instead of travelling normally, light can split into different components or change its direction and behaviour. This effect happens because the magnetic field alters the properties of the vacuum around the star, turning empty space into something that can influence light directly. For scientists, this creates both a challenge and an opportunity. It becomes harder to interpret what they observe, but at the same time it provides direct evidence of advanced physical theories. By studying how light behaves near magnetars, researchers can test ideas about the fundamental nature of space and energy that would otherwise remain purely theoretical. Magnetars are not just unstable in a general sense. Their instability is built into their structure at a fundamental level. The source of this comes from their magnetic field, which is not smooth or evenly distributed. Instead, it is highly tangled and twisted, both on the surface and deep inside the star. These magnetic field lines behave like stretched elastic bands under extreme tension. Over time, they continue to twist due to the star's rotation and internal motion, storing enormous amounts of energy. Unlike Earth, where stress can be slowly released through small, frequent movements, a magnetar has very limited ways to release this pressure. As a result, the stress keeps building without relief. This growing tension directly affects the crust of the magnetar. The crust is incredibly strong, often described as billions of times stronger than steel, yet even this strength has a limit. The magnetic forces pulling and twisting the crust are so intense that they gradually deform it. Instead of bending smoothly, the rigid crust resists until it suddenly breaks. When it does, the fracture is not like a typical crack. It is a catastrophic rupture across a dense, ultra-compressed surface. This sudden shift is what scientists call a starquake. In that instant, a huge amount of stored magnetic energy is released outward, producing powerful bursts of X-rays and gamma rays. What makes these events even more extreme is the process that follows the fracture. When the crust breaks, the magnetic field lines that were previously locked in place suddenly snap and rearrange themselves. This process, known as magnetic reconnection, releases additional energy and accelerates particles to extremely high speeds. These particles then emit radiation that can travel across the galaxy. The initial crack in the crust is only the beginning. The real energy release comes from the magnetic field rapidly settling into a new configuration. Another important aspect of this instability is that it does not happen just once. Magnetars can experience repeated stress cycles. After a starquake, the magnetic field continues to evolve, building up tension again over time. This leads to a pattern of smaller bursts and occasionally massive flares. Some of these flares, known as giant flares, are so powerful that they can affect space far beyond the star itself. Even from great distances, their radiation can interact with planetary atmospheres and disrupt electromagnetic systems. Despite observing many of these events, scientists still struggle to predict exactly when they will occur. The internal conditions of a magnetar are extremely complex, involving interactions between nuclear matter, magnetic forces, and rotational dynamics. Small changes deep within the star can lead to large, sudden outcomes on the surface. This sensitivity makes precise prediction nearly impossible with current models. Researchers rely on patterns, past activity, and indirect signals, but the exact timing of a major flare remains uncertain. In essence, a magnetar is never truly at rest. It exists in a continuous cycle of tension, fracture, and release. This constant instability is what makes it both fascinating and important to study. By observing how magnetars handle such extreme internal stress, scientists gain valuable insight into the behavior of matter and energy under conditions that cannot be recreated anywhere else in the universe. Look up at the night sky. It appears calm, serene, timeless. The stars twinkle in familiar patterns, giving the illusion of a universe at rest. But now you know the truth hidden among that tranquil sea of light are objects that defy imagination. Somewhere out there, cloaked in ordinary starlight, lies a dead star unlike any other, a magnetar. It is small, just a city-sized sphere, and silent to our senses. Yet inside it holds forces capable of bending reality itself. It does not consume like a black hole, nor does it explode like a supernova. Instead, it exists in a perpetual state of tension, its magnetic field coiled like a cosmic spring. Every crack in its crust, every subtle rearrangement of its magnetic lines, stores energy that could erupt across the galaxy in an instant. This is a star of extremes. Its very existence is a testament to the power and unpredictability of the universe. For the patient observer, it pulses slowly, a lighthouse of radiation sweeping the cosmos. For the unprepared, it is a reminder that distance does not guarantee safety. A single flare, even from tens of thousands of light years away, can reach across space, touching planets, altering atmospheres, and bending the fabric of reality itself. Magnetars are quiet, yet violent, invisible, yet undeniable. They wait, their energy building, their next fracture imminent, and in that waiting, they teach us the most profound lesson. The universe is not static. Its rules are flexible, its power immense, and its mysteries far from fully understood. Each magnetar is a reminder that even in the vast calm of space, extremes lie just beyond perception, waiting for the moment to reveal themselves and remind us that reality is far stranger than it seems. And so, as you let your eyes wander across the night sky, remember this: among the countless stars, some are silent, some are dying, and some, like the Magnetars, are quietly rewriting the rules of reality. They are cosmic time bombs, laboratories of extremes, and reminders that the universe is far more mysterious than we dare imagine. Someday, perhaps, we will witness one of these stellar titans up close, not to touch, not to survive, but to finally understand the raw, untamed forces that shape the cosmos. Until then, every starlight flicker carries a secret. Every shadow between the stars hides a story. And somewhere, deep in the galaxy, a Magnetar pulses waiting. Waiting for the next fracture, the next burst, the next reminder that the universe is alive with possibilities we have only begun to comprehend. Because in the end, the universe is not just out there. It is reaching in, challenging us, daring us to see beyond the calm, and reminding us that the most extreme monsters may not be the ones that devour, but the ones that quietly hold the power to bend reality itself.